Thank you. Yeah, so hi everyone. Today's talk is about finiteness of symbolic derivatives, or proof of finiteness of symbolic derivatives in Lean. I'll explain all the keywords here. Yeah, so I'm Kat, and my co-authors are Hendrik, Margus, and Gabriel. So let's get to the introduction. When I talk about derivatives, I mean Brzezowski derivatives of regular expressions. And the definition has a very nice inductive structure. Intuitively, it takes a character, an expression, and returns an expression which represents everything which is left after you chopped off the first character. And this function comes packaged with the notion of nullability, which is, again, a very nice inductive function, which tests whether the empty string is in the language of a given expression. And there has been many extensions to this definition, which have been applied in many decision procedures. But today, what we're interested in is the proof of finiteness. So remarkably, Brzezowski himself, back in '64, showed that the set containing all the iterated derivatives is finite, as long as you quotient it by an appropriate relation. And this relation is the ACI similarity, which very intuitively corresponds to the associativity, commutativity, and idempotence of the union operator, which allows us to remove duplicates and conclude the proof of finiteness. So in this work, we extend the proof to what we call symbolic derivatives. The derivative function does not take a concrete character. And instead of returning an expression, it now returns what we call a transition term or a transition tree. We prove finiteness by building an over-approximation for the set of all iterated derivatives. And the other symbolic aspect is the fact that our regular expressions operate over a symbolic alphabet, which is represented by a structure called an effective Boolean algebra. Intuitively, the transitions don't just carry single characters, but they carry predicates, which semantically correspond to sets of characters. And the final point is that we do not assume commutativity of union, which was one of the equations on the previous slide. And the reason for that is that there are two different match semantics that exist in the literature, PCRE and POSIX. And the easiest way to demonstrate the difference is by example. If you have an expression like A or AB star and the following string, the PCRE match will prioritize the leftmost alternative. Therefore, the match just contains the prefix A, whereas the POSIX will consume the entire string. And under PCRE semantics, union doesn't really behave as we would like it, and commutativity does not hold. And the reason why it's interesting is because majority of industrial regular expression engines actually implement PCRE. Okay, so I mentioned that we're working with regular expressions with lookarounds. Two aspects to highlight here. As I mentioned, we don't have concrete characters, but we have predicates. Again, just a small example. If you have a predicate, syntactic predicate called psi upper, the semantics of it is that it corresponds to a character set representing uppercase Latin letters. And the other extension is that we have lookarounds. So we account for both positive and negative look-aheads and look-behinds. And I'll talk a little bit more about the semantics of these operators. So the semantics for lookarounds complicate things a little bit, since the conditions in lookarounds don't really consume any characters. The matches are empty, but they describe a context in which a match should occur. Again, let's look at an example. If you have the string, instead of talking entire strings here, we will have to introduce some terminology. One is a location. So a location is just a pointer into the string, indicating where we are in this particular string. And in our setting, this is important because both the derivative and nullability functions take a location rather than a character. because there is this local notion of context. And now, in order to define the semantics for this class of regular expressions, we need to also mention the notion of span, which is, in other words, 2 pointers into the string, indicating where the match begins and where it ends. And then you have the left and the right context, meaning the remaining parts of the string. So I'll just concentrate on one case for the semantics. Here we have the look ahead. And as I mentioned, we cannot just talk about words. Here we talk about spans. And the semantic characterization of this is the fact that the match itself is empty, but we assert the existence of a match for the body of the look ahead later in the string, somewhere in the future. So if you look at this example of look ahead, which contains the predicate for uppercase letters in this given string, then the only valid span for this expression is going to be of this form, where the middle part is empty, so it's an empty match. And on the right-hand side, you can see that the first letter, the first element, is precisely an uppercase letter, which means that there is a future match for the body of the look ahead, and then followed by top star, meaning anything. So it's a continuation which will match anything. Now, talking about symbolic derivatives. So a symbolic derivative is a transition term. So it's a tree. I have the type up here. And I would like to motivate it with an example first before going to the next definition. So if we have two atomic predicates corresponding to the singleton letters, and we take their disjunction or their union, taking the symbolic derivative of this expression will produce the following tree, where the nodes are, in this case, look-aheads containing the predicates, and the leaves intuitively correspond to all the potential next states that the derivative function can take you to. And now, how should we think about it? So we should think about the symbolic derivative as partial evaluation of the regular derivative, in the sense that all the nullability conditions have been delayed. But if we look at the expressions in the leaves here, we can see that the first three expressions are essentially equivalent to epsilon. And if you think of starting from the root of the tree, evaluating the condition based on whether it is nullable or not, and then taking the right path if it is, or taking the left path if it's not, we will essentially get epsilon as the next state if either of the disjuncts is nullable. And then the fourth, the red leaf here corresponds to the state which has the bottom expression, meaning that neither of the disjuncts are nullable. So a transition term is really just a function which takes locations to regular expressions. And the intuition is that we postpone all the nullability tests. Now, I said it's a notion of a partial evaluation of the regular derivative. So we can actually define the evaluation function for these trees. We have to take a location, a tree, or a transition term, and the return type is just a regular expression corresponding to which leaf the function leads us to. And you can see that here, essentially we have a decision tree where the condition is testing whether the current expression in the condition is nullable or not. And we take these paths to the next state. Now I can define the symbolic derivative definition. And there's two interesting cases, which are the predicate. No, I don't think it works. So the predicate case and the concatenation case. Maybe I can do this. So in the case of predicate, we build a tree where in the node we have a look ahead with the predicate as the body of the look ahead, and then we have the epsilon and the bottom. So if we think of the intuition that when evaluating these trees, we test the nullability of the condition, we can see that if it's nullable, indeed, we end up in a state which is nullable, and if it's not, we end up in a state denoted by bottom. And the case for concatenation, it follows precisely the standard definition of derivative in a way that we have to make a choice depending on whether the left side of the concatenation is nullable or not. And that's why the condition here is exactly the left-hand side. And the other operations are standard, but lifted to these trees. And now we show equivalence of the symbolic definition and then the sort of concrete location-based derivatives. So if we take the transition term and evaluate it on a location, it corresponds precisely to the standard derivative definition, which allows us to work entirely with the symbolic variant. So we would like to talk about the set of all iterated derivatives. So far, I can define this wrapper function step, which applies the symbolic derivative. So we get a tree, and then we simply collect all of the leaves because they exactly correspond to the potential next states. This step function is well behaved with respect to all of the operations, so they just propagate all the way to the leaves. And of course, it's not enough to say what the immediate derivative is. We need to be able to iterate this for words of length n, and this is why we lift this function step to steps, which is the computation of the nth derivative. So it now takes a parameter which is corresponds to how many times we would like to iterate the derivative computation. So I mentioned briefly the Berzovsky approach, and there exists another variant of the derivative definition, anti-Mirov derivatives correspond to a deterministic automaton construction. Anti-Mirov derivatives correspond to a non-deterministic variant. So the derivative function now returns a set of expression introducing non-determinism in this way. And actually, the proof of finiteness for anti-Mirov derivatives is extremely straightforward, but the more complicated part is dealing with the extended operator. So in our approach, we wanted to take inspiration from anti-Mirov style proof and extend it to our setting. I say that we're going to have to talk about some similarity relation, and on the very first slide, I also mentioned that there are two different match semantics. So first, there are some helper functions to help us with the reasoning up to some relation, which is list membership, inclusion, and equality. But really, we instantiate this relation with one particular one, which is the ADI similarity. It's defined almost exactly like the one that I had before, except that instead of commutativity, we have this slightly different notion of right deduplication, because we would like to also extend this result to the setting where we don't have commutativity of union. Going back to the proof of finiteness for anti-Mirov, I say that it's straightforward. Why is it so easy? Well, you can define this function called support, which allows us to reason about the set of all iterated derivatives. And the interesting case here is the fact that when we have an expression containing the union, this function essentially splits it into sub-expressions. So there will not be an element of the set which has union as the topmost operator. And indeed, this the set of all anti-Mirov derivatives is contained in the set. So the proof of finiteness really reduces to proving finiteness of the support, which follows by induction on R. And notice that we're not doing any quotienting here because this ACI notion is built into the set representation. And now can we do something similar for Berezovsky-style derivatives? So far, I have defined a way to reason about immediate and next step derivatives. So we have a way to talk about all reachable states from a given expression. How do we show finiteness of the set? Our solution is to define a finite over approximation modulo this ADI relation. Some intuition is, I'll look for this example. So if we start with an expression of the form A or B concatenated with C, the pieces here corresponds precisely to the over approximation that we would like to define. And what we want from this definition is to split the expression into smaller parts in such a way that any iterated derivative can be reconstructed from this list. And indeed, we can see here that if we split the union, so each sub-expression is contained in pieces. So we would like to have all derivatives represented as a union of this function. A few more comments before I move on to the definition. Since we don't have commutativity, the reasoning becomes a little bit more complicated because we have to consider all permutations of a given list. So we have this O+ operator, which computes all permutations of all sublists and then folds them with plus. And the other small note is that when dealing with intersection, we have to compute the Cartesian product of the two sets and then essentially fold it with, use the binary operator in order to apply it to each pair, which is the most computational part as well. So this is our over approximation. And since we were trying to follow the strategy of the support function, the case for union precisely corresponds to that because we're splitting it into sub-expressions in the same way, so that there will not be a piece which contains the union as its topmost operator. And the rest of the cases are pretty straightforward. I mentioned that for intersection, we have to do this computationally intensive operation. And the O+ is here because we are considering this slightly more restricted notion where we don't have commutativity. So now we can move on to the main theorem. The key properties of pieces which are used for the proof of finiteness. First is a reflexivity-like notion, where essentially we can break apart any expression into pieces and then reconstruct it using sum so that these two things are equivalent. The second thing is a transitivity-like notion for pieces, so that we start taking pieces, but then we don't exit the set. We just keep reusing the same pieces again. And the most difficult part is the one-step reconstruction, which essentially relates the step, which is the actual derivative function, and the pieces, so our over approximation. And this allows us to state the main result, where every iterated derivative of R can be reconstructed as a sum of pieces. So the theorem is that for each R, we can come up with a list which is finite by construction. And no matter how many times we iterate the derivative function with our steps, we will still stay in this list. And our witness here is O plus of pieces. So there's two main works that are highly related because they also formalize the first paper formalizes the Berzowski's original proof, and they come up with a more exotic notion of finiteness. And the second work is formalized in Isabel, where they consider just the standard grammar of regular expression, but they also formalize the proof of finiteness. But both of these use, they define a normalization function, which essentially has the ACI equations built into it from the very start. And then they have two versions of it. One is just a vanilla ACI, and one is which has more aggressive simplifications, because in practice, you want to have a more performant algorithm. So our strategy is, of course, to instead go down the route of having an over-approximation by following sort of the Antimirrov's definition and combining the two approaches. And one interesting question is, once you have the finiteness, which simplifications rules can we actually include that preserve this finiteness result? Because as I said, you would like to include many more simplifications in practice. So any function, any simplification function here, which is non-increasing, intuitively meaning it does not introduce any new pieces, will be accepted. So it will not break the finiteness result. And here I show some simplifications which are allowed. And I would like to highlight two slightly more interesting cases. So the construction of this over-approximation very closely follows the syntactic construction of the derivative, which kind of leads to some interesting simplifications which are allowed. For example, R concatenated with S can be simplified to S, which in terms of language semantic doesn't make sense, in the same way that the union can be simplified to either the left or the right part. So we have to be careful about which simplification rules we actually would like to include according to what makes sense based on the language semantics. And just one simplification which is not allowed is something of this form, which again, if you instantiate S with epsilon here, for example, which would be a reasonable rule, but it's not such a big problem because, as I said, there is this syntactic correspondence between pieces and the actual derivative function. So we would actually like to have the simplification rule which is allowed, where the epsilon is on the left-hand side, not on the right-hand side. Okay, so yeah, we have a proof of finiteness for this extended set of regular expressions with lookarounds using symbolic derivatives. It's about 2,000 lines of code, and we build up on some previous results. We showed which simplification rules can be applied and preserve finiteness. So there is no assumption that the alphabet is finite, and since we're working modulo an alphabet algebra, it's actually a little bit more general in the sense that the alphabet algebra itself can be undecidable. And one thing that we haven't done, but would like to have, is we need this proof of finiteness for many algorithms involving termination proofs, not only for regular expressions, but for some classes of logics for which derivative function can be defined. So it would be nice if this effort could be more modular, but this is not something that I can present here. Thank you. That's all.